Since today is our first class in the trimester, we're going to start a completely new topic, which is waves. So today we're going to look at the introduction to waves, how they can be divided into different types, their properties and their characteristics, and then in following classes we're going to look at specific types of waves like light waves and sound waves. So first I wanted to define what is a wave. So we know what a wave is. If we see one, we identify it, like the waves in the ocean, a wave on a string, but we usually don't know how to define it. So a wave is actually called a disturbance that moves and carries energy with it as it moves forward. So I'm going to write that down. Okay, so when we see, for example, a wave in the ocean, it's not the water, like that same piece of water that is traveling from one end to the ocean to the other. It's actually the energy that is moving along the water, creating waves as it goes. So if you've ever seen something floating in water, the waves don't usually move the thing very much. They just move the thing up and down. So when you're floating in the ocean and a wave passes through you and through the water, you go up and down, but you stay sort of in the same position. So that's why the wave is not the moving thing, it's the energy that moves through that thing. Now, they can be divided into two types according to one characteristic and into two other types according to another characteristic. So we have mechanical and electromagnetic. And electromagnetic waves. So mechanical waves require a medium to travel through. So the definition of this is that they require a medium. So what that means is, for example, if you have waves in the ocean, if you take away the ocean, there are no longer any waves. If you have a wave on a string, if you take away the string, you don't have any waves. With sound requires air or something to vibrate in order to move through space. So if you take away the air, like in space in a vacuum, there won't be any sound traveling, so there won't be any waves traveling. So all of these are examples of mechanical waves. So that includes water waves, that includes waves on a string, waves on a spring or resorte, sound, many other types of waves. This is why, because sound is a mechanical wave, astronauts can't talk in space. I mean, they can talk, but they won't make any sound and no one will hear them. That's why we can't hear the sun, for example. The sun has thousands of millions of explosions every second, and no matter how close you get to the sun, you will never hear them because there's no air, there's no medium to transport the sound towards your ears. So that's why astronauts, they talk through radios. They need a radio to be able to hear each other because radios are the other type of wave. So the other type of wave is called electromagnetic wave, and it means that it doesn't require a medium, that it can travel through vacuum. Travel through a vacuum. Vacuum is vacío, right? So these types of waves are all part of something bigger called the electromagnetic spectrum. In order of least energy to most energy, those are radio waves, microwaves, infrared light, visible light, ultraviolet rays, X-rays, and gamma rays. But just for now, you need to know that there are some waves that need to move something, atoms, pieces of string, pieces of water, something to move so that they can move through it. And some waves, which are the electromagnetic waves, which don't require a medium and they can travel through space. That's why we see the light from the sun. Another way to divide waves is by how they oscillate. So oscillate is when the wave moves up and down, up and down. Each time it goes up and down, it's one complete oscillation. Up and down, one complete oscillation. So how they oscillate. Some of them are called transverse waves. And others are called longitudinal waves. So transverse waves means that a wave is like this, like the waves in the ocean. The direction of oscillation is up and down, up and down. That direction is perpendicular to the direction in which the wave is traveling. So for example, the wave is like this. It's traveling this way, like towards, I don't know, the shore, if this is a wave in the ocean, but the oscillation of every single point in the wave is up and down, right? So the oscillation is perpendicular to the direction of propagation, which means the direction the wave is traveling towards. So these are perpendicular. Instead, in a longitudinal wave, the direction of propagation could still be to your right, but the direction of oscillation will also be right and left, so forward and backward as the wave moves forward. So for example, suppose you have a spring. Resorte looks something like this. And you push it on one end and then take it back, and push it and take it back. That's going to cause a wave to propagate like this, right? So at some point, these are going to be closer together, so it's going to look something like this. And these are going to be further apart, so it's going to look something like this, right? So you're going to have parts that are very compressed and parts that are very expanding. Those are longitudinal waves. So the direction of propagation is parallel to the direction of oscillation that every ring of the spring has. So here those two are parallel, and here they're perpendicular. So now I'm going to test my YouTuber skills and cut now to a video showing you a string, waves on a string for transverse waves, and waves on a big spring for longitudinal waves. Okay, so I have two types of materials that I'm going to use to create waves. So I'm going to go out of frame and show you what a transverse wave looks like. And with this, we can create a longitudinal wave. So that means like this. Or like this. Or like this. Transverse, transverse, and longitudinal. Anyway, like this. Okay, so hopefully you were able to see something interesting in that clip, and if not, do it in person. But basically what you saw is that you can move a string either up and down or right and left while the wave propagates forward. So the direction of oscillation in any direction is perpendicular. It's something like this, it's perpendicular to the direction of propagation. And in the longitudinal, when you have a spring, the direction of propagation is parallel to the direction of propagation of the wave. Now I'm going to tell you which of these are each. So actually all electromagnetic waves are transverse waves. So these are all transverse. Transverse. And these are mostly all transverse, except for sound. So these three are transverse, and this one is longitudinal. So most waves are transverse. Sound is the most common and known example of a longitudinal wave. So the way that sound works, we're also going to look at it more specifically, I think, in 2 or 3 classes, is that when you talk, you make the molecules of air in front of your face vibrate forward and backward. And they will vibrate forward and backward, hitting the next group of molecules and the next until they reach someone's ear, and they make the air beside their ear vibrate, and that's what you can interpret as a sound. Now let me erase all this and move on to characteristics of waves.